Welcome, ladies and gentlemen, to what I like to call engineering's dirtiest secret. And I mean that quite literally. Today, we're diving into the peak strength paradox, or, as I affectionately call it, why we measure something just to completely ignore it. Now, take a look at these two images. On the left, we have a beautiful, pristine rock specimen. Smooth, cylindrical, perfect. It's basically the supermodel of the rock world. And on the right? That's reality, folks. That's Mother Nature's version. Fractured, weathered, and more complicated than your last relationship. Here's the kicker. We spend thousands of dollars testing that perfect little specimen. Get a number that makes us feel all warm and scientific inside, and then we throw it out. Well, not literally, but we certainly don't use it for design. Why? That's exactly what we're about to unpack. So buckle up. This is going to get rocky. All right, let's get serious for a moment. When we design foundations on rock, whether it's for a bridge, a dam, or your mother-in-law's house that absolutely must be built on a cliff, we deliberately ignore that shiny UCS number we got from the lab. And this isn't because we're lazy or forgot our engineering fundamentals after too many Friday happy hours. No, no, no. This is actually one of the most sophisticated decisions we make. You see, there's a Grand Canyon-sized difference between that perfect lab specimen and the actual rock mass sitting in the ground, minding its own business for the last few million years. Think of it like this. Testing a lab specimen is like judging someone's driving ability based on how well they play Mario Kart. Sure, they can nail those turns on Rainbow Road, but can they parallel park in downtown Manhattan? That's a whole different ballgame. So today we're building our case on 5 critical factors. Think of them as the 5 pillars of why that lab number is lying to you. We've got the unrepresentative nature of the sample, the brittleness problem, scale effects, serviceability requirements, and long-term degradation. By the end of this presentation, you'll understand why ignoring the peak strength isn't just smart, it's absolutely essential. Let me introduce you to what I call the tale of 2 rocks. And yes, I just made a Charles Dickens reference in a geotechnical presentation. You're welcome. On the left, we have the lab specimen. Look at this little guy. He's been carefully extracted, lovingly prepared, ground to exact dimensions, and stored in a climate-controlled environment like some kind of geological celebrity. This specimen represents rock in its absolute best state. It's Instagram-filtered, airbrushed, woke up like this version. It's been to the spa, gotten a massage, and is ready for its photo shoot. Now, feast your eyes on the right, the in situ reality. This is what rock actually looks like in nature. It's got joints, fractures, bedding planes, faults, weathered zones, and probably a family of groundhogs living in there somewhere. This rock has lived. It's been through freeze-thaw cycles, earthquakes, erosion, and millions of years of geological drama. This rock has stories, people. And here's the million-dollar question. Which one do you think controls how your foundation behaves? Spoiler alert, it's not the pampered lab specimen. It's the fractured, weathered, complicated mess on the right. That's reality. That's what we're actually building on. So designing for the perfect specimen and expecting it to represent the rock mass is like ordering a 5-star meal and expecting your leftovers to taste the same 3 days later. The difference is substantial. Reason number 1. The lab sample is what I like to call a flawed witness. And if this were a courtroom drama, which, let's be honest, engineering should be more exciting, this witness would get thrown out faster than you can say, "Objection, Your Honor." Look at this diagram. See that foundation footing up there? When you load it, the stress doesn't just go straight down like a laser beam. Oh no, it spreads out in what we call a stress bulb, which sounds delicious but is actually just physics. This stress bulb affects a huge volume of rock beneath the foundation. Now, what's lurking in that volume? Bedding planes, joint sets, and, oh look, a major fault line. It's like a geological obstacle course down there. The behavior of this entire system is controlled by these discontinuities, these breaks, cracks, and fractures. And that tiny little UCS lab sample sitting over to the side? It completely misses all of this. It's like trying to understand New York City traffic by watching one guy drive around an empty parking lot in Iowa at 3 a.m. Sure, you learned something about driving, but you learned absolutely nothing about the chaos that is rush hour in Manhattan. The peak strength of the intact rock between the fractures? Utterly meaningless when the fractures themselves are calling the shots. It's not the rock material that fails, it's the rock mass. Big difference, folks. Huge difference. Reason number 2 is where things get a little explosive. And I don't mean that metaphorically. I mean rocks literally fail in a violent, brittle, did someone just set off fireworks in the lab kind of way. Take a look at this stress-strain graph. That green line climbing up? That's our stable design zone. Everything's predictable. Everything's safe. We're in control. Life is good. We're sipping coffee, checking our emails, living our best engineering lives. But see that peak at the top, marked with the big red X? That's what I call the "oh no" zone. That peak represents the exact moment when the rock says, "You know what? I'm done." And when rock is done, it doesn't gradually retire. It doesn't give 2 weeks' notice. It quits. Immediately, catastrophically, with extreme prejudice. Look at that dashed red line dropping off the cliff. That's the catastrophic capacity loss. The rock goes from, "I'm holding this building up just fine," to, "Nope, not doing this anymore," in milliseconds. It's brittle failure, folks, and it's terrifying. Now, imagine designing a structure to operate right at that peak point. That would be like tightrope walking over Niagara Falls during a windstorm while juggling chainsaws. Sure, technically it's possible for a brief moment, but one tiny miscalculation and, well, let's just say your insurance company is going to have some questions. Sound engineering practice says, stay far, far away from that peak. We want to hang out in the stable zone where things are predictable, where we can sleep at night, and where buildings don't suddenly decide to introduce themselves to the basement. Reason number 3 is one of my favorites, because it completely defies what people expect. It's the size matters principle, but not in the way you think. Here's the thing. Rock strength is not a constant property. It's not like the speed of light, or the number of times your boss will ask, "Can we talk?" on a Friday afternoon. No, rock strength actually decreases as the volume of rock increases. Mind blown. Look at these numbers. At lab core scale, we're measuring 100% strength. That little specimen is showing off, flexing its muscles, being all impressive. Move up to block scale, and suddenly we're down to 50% strength. Half! And when we get to rock mass scale, the actual volume beneath your foundation, we're down to a measly 15% of that lab value. Why does this happen? Statistics, baby. As the volume of rock increases, the probability of encountering a strength-reducing defect, a crack, a joint, a weak layer, a spot where water got in and threw a party, increases exponentially. It's like searching for typos. In a text message, you might not find any. In an email, you'll find a few. In a 300-page thesis? Oh, they're everywhere. So that beautiful UCS number from your lab test? That's the strength of a tiny, perfect volume. The real rock mass beneath your foundation? It's only got about 15% of that strength. This is why we can't have nice things, people. This is why we need factors of safety. This is why engineering is fundamentally pessimistic, because geology loves to surprise us, and those surprises are never the good kind. Reason number 4. We're not just trying to prevent buildings from falling down, we're trying to prevent them from being annoying about it. Let me explain. On the left, we have the dream, serviceable design. Look at that building. It's stable, it's level, the doors open properly, the windows don't crack, and the owners aren't calling us every 3 months asking why there's a new crack in the drywall. This is success. This is what we live for. On the right, unserviceable failure. That building is leaning like it's had one too many at the office party. The foundation is cracked, the ground is failing, and somewhere a structural engineer is updating their resume. Here's what people don't understand. A foundation doesn't have to collapse to fail. If your building settles too much, or settles unevenly, it's failed, even if it's still standing. Doors won't close, pipes break, people get dizzy walking down hallways. It's a disaster, just a slow-motion one. This is called serviceability, and it's absolutely critical. We have strict criteria. Limit total settlement. Limit differential settlement. Keep everything predictable and stable over the entire design life of the structure. If you design for that brittle peak strength, you're basically designing for technically not collapsed. That's not good enough. We need to design for long-term, stable, predictable performance. We use allowable bearing pressures and the rock mass deformation modulus to ensure the foundation behaves itself for 50, 100, 200 years. Because here's the thing, gravity is patient. Gravity will wait. And if you cut corners, gravity will find them. Every single time. Reason number 5 is all about time. And folks, time is not kind to rock. I know, we think of rock as eternal, unchanging, the foundation of the earth itself. But rocks age, just like the rest of us. They just do it slower and complain less about their joints. Look at this timeline. At time 0, we've got that pristine lab core showing peak strength. It's young, it's fresh, it's full of potential. Fast forward 50-plus years, and we've got a fractured, weathered rock mass with seriously degraded strength. What happened? life happened. Let me run through the greatest hits of rock degradation. First, we've got weathering and moisture sensitivity. Water gets in there and starts breaking down minerals like a slow-motion acid bath. Then there's water pressure in joints, which acts like a hydraulic wedge, prying things apart. We've got creep and stress relaxation, where the rock slowly deforms under constant stress, like a teenager's posture. Freeze-thaw cycles expand and contract water in cracks, playing the world's slowest game of let's split this rock apart. And chemical weathering? That's where minerals literally dissolve or transform into weaker minerals. All of this happens after your lab test. That UCS value you measured? That's based on a fresh sample tested in minutes or hours. It has no idea what 50 years of freeze-thaw cycles feel like. It's never experienced a drought followed by a flood. It's never been through decades of groundwater chemistry changes. Using peak UCS for long-term design is like hiring someone based on their college transcript and assuming they'll perform exactly the same way 30 years later. People change. Rock changes. We need to design for reality, not for the idealized moment captured in a lab test. Time makes fools of us all, including rocks. All right, let's bring this all home. If we were in court, and I'm picturing an engineering courtroom here, complete with tiny gavels and briefcases full of soil samples, here's our closing argument. 5 reasons why peak UCS gets benched like a third-string quarterback in the fourth quarter. 1. It's not representative. The rock mass and intact rock are not the same thing. Saying they are is like saying a forest is just one tree repeated a bunch of times. Joints control the behavior, not the intact rock between them. 2. It's brittle and dangerous. Peak strength is unstable. Failure is sudden, violent, and catastrophic. Designing for this is like planning your retirement around winning the lottery. Sure, maybe it works, but probably not. 3. Scale effects are brutal. That rock mass is way weaker than your lab specimen. We're talking 85% weaker at scale. 85%. That's not a rounding error, folks. That's a completely different material. 4. Serviceability trumps capacity. Foundations have to prevent deformation, not just avoid collapse. We're setting the bar higher than technically still standing. 5. Degradation is inevitable. Peak strength is a snapshot of a perfect moment that will never exist in the field. In the real world, rocks degrade, conditions change, and time is undefeated. Put it all together, and you see why we don't just ignore peak UCS. We run from it. We want nothing to do with it for design purposes. It's an interesting data point for classification and reference, sure. But for actual foundation design? Nope. Hard pass. We're going with the rock mass approach. So if we're not using peak UCS, what are we using? Great question. Welcome to the professional approach, where we actually deal with reality instead of pretending rock is perfect. Instead of relying on one misleading number from a lab test, we use a holistic approach that characterizes the entire rock mass. It's like the difference between judging a restaurant based on one Instagram photo versus reading 500 reviews checking the health inspection records, and visiting during a dinner rush. Much better information. Here's what we do. First, we characterize the rock mass. This means using rock mass classification systems like RMR and Hook-Brown. These are frameworks that account for all the messiness: joint spacing, joint condition, groundwater, weathering, the whole 9 yards. We analyze joint shear strength and orientation because we care about how those fractures behave. We determine allowable bearing pressures based on the actual rock mass, not fantasyland intact core values. And we apply appropriate factors of safety because, again, geology loves surprises. Then we move into analysis and design. We're using sophisticated tools, proper engineering judgment, and enough coffee to fuel a small rocket program. The result? A stable, predictable, and ductile response. Not a brittle, catastrophic, "Why is the building sinking?" response. A good response. The kind of response that lets you sleep at night. The kind of response that means your building is still standing in 100 years, and some future engineers looking at your design saying, "Wow, they really knew what they were doing back in 2026. This is real engineering, folks. This is why we get paid the medium to large bucks. Because anyone can measure a number. But it takes a real engineer to know which numbers actually matter. And now we arrive at our guiding principle, the philosophical foundation, if you will, of rock engineering. Are you ready? Here it is. The ultimate strength of a perfect lab specimen is an academic data point. It's interesting. It's useful for reference. But it's academic. It exists in the realm of theory. The effective strength of the fractured, weathered, and large-scale in situ rock mass is the engineering reality. That's what matters. That's what's actually out there in the ground, supporting your structure, doing the real work. And here's the money line, the one you should write down, tattoo on your forearm, or at least put on a Post-it note on your monitor. We design for the ground as it truly is, not as we wish it to be. This is the fundamental honesty of geotechnical engineering. We don't get to pick our materials. We don't get to specify high-quality rock with no fractures and perfect strength properties. We get what Mother Nature gives us, and Mother Nature is rarely generous and never perfect. So we measure reality, we characterize it, we understand it, and we design for it, with all its flaws, all its complexity, and all its wonderful, terrifying unpredictability. Because at the end of the day, the ground doesn't care what your lab test said. The ground is going to behave the way the ground behaves. Our job is to understand that behavior and design accordingly. And that, ladies and gentlemen, is why we ignore peak UCS. Not because we're bad engineers, but because we're good ones. Because we know the difference between data and reality, between theory and practice, between what rocks can do in a lab and what rocks will do under a billion-dollar structure. Thank you for attending Engineering's Dirtiest Secret. May your foundations be stable, your settlements be minimal, and your rock masses be well characterized.